Welcome to the second session of the CUDA mini course. Can everyone hear me, and can you see the screen?
Yes, yes.
Great. So, in today's session, I first want to show you an analysis of a bug in the MSM that we found and fixed last week as a continuation of the debugging methods I've shown you in the last session. And then we will dive into some optimizations methods using Insight Compute and other techniques. So we had a statistical bug in the MSM, which occurred with the same input. We just ran the same test multiple times with the same input. And after around 2,000 times, the MSM returned an incorrect result. So this bug is difficult to find because it's difficult to reproduce. Each time you need to run it many times until the bug is there. And also, when we tried to narrow down the problem, then sometimes the bug didn't occur. So we followed the following steps. First, we found the most simple case that still has the bug. Then I checked the intermediate results to find the problematic kernel. So I tried to add some prints between the kernels and check the intermediate results. Some of the times when I tried to print, it meant that the bug didn't appear. So the actual prints made it impossible to debug. This happened when I copied some memory from the device to the host. Yeah, exactly. Schrodinger's bug. Yes. But instead, when I added some prints within the actual kernels, then the bug still occurred. So that enabled to debug. Once I discovered the correct kernel, I printed the read and write addresses to see if there's any threads that run over each other. And indeed, I discovered that this was the read and write pattern. We can see the blue thread. It reads from these two addresses and then writes to the first address. And the orange one reads from these two, adds them together, and writes to this address. So can anyone spot the problem here?
Is it the same memory at the beginning and the end?
Yeah, it's the same memory.
Two concurrent threads. So the blue one needs to run before the orange one.
Yes, exactly. So one thread reads and the other thread writes to the same address. So most of the time, the blue threads runs before the orange thread, but some of the time it's the other way around, and then the result is incorrect. So this is a thing you can find in a lot of kernels, multiple threads reading and writing. So the solution for this needs to be one of the three. Either you work out of place, meaning that you need the memory that you write to be different than the memory you read from, and then it will be fine. The second solution is to do thread synchronization, meaning you can add the sync thread command after the read. So you make sure that all the threads have read before they write. but that is possible only for the threads within a single block. And in this case, these are threads of different blocks, so they cannot be synchronized.
Would it also hamper performance?
The synchronization, and not necessarily, but it can.
It's always, I think it's always better to, if you can work without syncing, then you should prefer to work without syncing, but sometimes syncing doesn't really, lower the performance a lot.
Yeah, I mean, if you
But it's always
can,
like
if you
an
can
instrument
avoid it,
instrument,
yes, right.
So,
Yes, and the third thing you can do is to change the axis pattern. So make sure that every thread writes only to where it's read from. And that's what I did to fix the bug. So now we have some gaps in the memory, but it's fine. We only make use of these memory addresses, and that solved the bug. So
if you have some kind of subsequent step where you need to take data and it is like separated across blocks, it's going to be less so, or it doesn't affect efficiency in terms of accessing data, it's not continuous.
if I didn't understand the
So
question.
now this, let's say you write this data back, right, and you have subsequent step where you take 4 and make it 2.
Yes.
that's what's happening here.
Now, because there's a gap in between, right? So it needs to know that like there's empty 4, there's empty, and then there is this one. So if it is like this, is it okay in terms of like?
Yes, it's okay.
It need to be
It's,
continuous.
so yeah, the best, it would be best if it would be continuous, but this just means that we need to gather the final results from different addresses at the end. That's why at first it was like this, but this has this problem.
You can achieve coalescing like that, and that's the main thing. You're able to achieve coalescing.
Mm-hmm. Yes, I will talk about coalescing mainly in the next lecture. But okay. So any other questions regarding this? Okay.
So far, what we are talking here is still the threads connected to shared memory.
No, this is the global memory.
Global.
Just reading and writing from the global memory. So now we move on to an example.
That's actually a question. Can this happen on the shared memory?
Yes.
It can, right?
Yes, it can happen also with the shared memory if you don't synchronize the threads.
Yeah.
So as an example of a kernel that we would like to optimize, I want to look at the bucket, a similar kernel to the bucket accumulation kernel from the MSM. So moving on to VS Code. Yes, so we have here a kernel that receives pointed to an array of buckets, an array of indices, and an array of sizes of the buckets. So what we have essentially is an array of some type, and we want each type to add, actually to multiply by the size. So let's say we have 1 in the first bucket, and we want to multiply it by 3, and then we have 2, and we want to multiply it by 7. So each value we want to add to itself size times. It's a different value for each bucket. So the indices is just an array of the thread indices, of the bucket indices, and it holds the sizes is an array of the sizes you will see when I initialize them in the test that so the indices is just an array of 1, 2, 3, 4, and so on, and the sizes I generate a random value from 0 to 20. And the buckets contain a random scalar or point depending on the test T type. So what this kernel does, you can see that each thread deals with a single bucket. And it runs a loop that goes from 0 to the corresponding size. And then it takes the bucket index and it adds the value together with itself, the number, size times. So is the functionality clear of the kernel? Great. And now, so the kernel actually it is correct and it does what I want it to do. But how do I know if it's optimal, if it gives good performance? So the first thing I want to do is to check to measure the time that it takes this kernel to run. So let's go over the test file. Again, I choose here the type of the type of the object that I want to test. So now I test the scalars. And now, when you want to measure the kernel time, then it's best not to do it using the C library for measuring time, because the GPU isn't in synchronization with the CPU. So it's best to use what's called the CUDA events. So what I do is I define 2 events, start and stop, and then I use the CUDA event record function to start recording, and after the kernel I use the CUDA event stop. Then I use the stream synchronize, and I use the event elapsed time to measure the kernel time. And then I print the time. So this is just the preferred way to measure the kernel time. And another important thing is to do a warm-up run, because most of the time the GPU actually needs to warm up before it achieves the best performance. It has multiple reasons that are actually described here. So the first launch of a kernel could be slower than the further runs because of these reasons. Just-in-time compilation, transfer of kernel to GPU memory, cache content, and so on. So it's always best to do a warm-up run to get the actual number that it would be in the end when it runs in an application. That's why I just run the kernel once before I do the actual measurement. So that's how I measure the kernel time. And once I run it, then I get this time of 0.3. Yes, 0.3 millisecond. So would you like to tell me if it's a good time or a bad time, or how would we know if it's good or bad? Huh?
It's that low. your specs? What are your requirements?
Yes, exactly. So how do I know if it's a good result on the GPU or not? Any ideas?
You can
By,
see utilization
Utilization, how?
with the program you showed us last week. Insight.
Right. So I cannot do analysis with Insight systems or Insight Compute, but is there a way to do it without the analysis programs? So actually, there is a way, and this is each kernel is usually either memory bound or compute bound, meaning either the computation takes most of the time or the memory takes most of the time. And how can we find out which is it? So actually, I wrote a memory baseline kernel and the compute baseline kernel. So in this kernel, I take out all the computation, and I want to see what's only the memory copies. How much does this take? So in this kernel, I just have two arrays of buckets, and I just copy from one to the other. So this is the memory baseline. And if I run this kernel, then I get let's see what I get. I get 0.1. So it's much faster. And when I run the compute baseline, so actually, how do I write a compute baseline kernel? It's a problem because if I don't read and write to the memory, then I don't have anything to compute on. And also the compiler can just remove the compilation, the computation if I'm not doing it on real data. So what I do is I add a loop inside the kernel to increase the amount of computation, and then the amount of memory copying would be very small compared to the computation. So actually, I do the computation 100 times. So the result that we get will need to be divided by 100. So if I go back to the kernels, to the test, and now I run the computation, then I get, you need to divide it by 100, then we get actually 0.05. So actually, this kernel is worse than the compute and worse of the memory. So yes, and also less than the sum. So we know that something is bad with how we wrote this kernel. So before I go to the analysis programs, maybe by just looking at the code, maybe can someone tell me what's the problem?
Is it copying buckets indices twice?
It's copying. What do you mean?
It shouldn't be like a.
Could a compiler have skipped the memory bound operations? Because it sees that it's the exact same expression on both the right-hand side and the left-hand side.
The exact same expression.
In the memory bound kernel. Here.
Here? No, it reads from bucket 1 and writes to bucket 2.
Oh, I didn't see that.
Yes, but right, it would skip if it would be the same. But in the original kernel, yes, there is a problem with this line, actually.
Maybe it's having it needs more time to to make sure that the writing does not override the read data because it's the same address.
It has to
Um,
temporarily store the results somewhere, right? Like it has to take something, add, and then put it back in the same position.
yeah. So where does it put back the results?
Every time.
For each,
So where does it put
Maybe.
back the result? How this is written here?
in a single thread,
It puts it back here, which is global memory.
Ah,
Which is what?
Which is global memory.
So you maybe could take it from the global memory, edit size times, and then put it back to the global memory.
So it means that
Uh-huh.
the loop should actually run in shared memory and then go back to the global memory.
So yeah, the correct way would be exactly it should save the temporary result in a register. Like so. We define a variable which will be in register memory, and then all the additions will be performed in the register space, and only the final result we will write back to the global memory. Yes, so let's say that we
Okay, how do you know which is, I mean, how do we understand which is the register memory variable? When you define something like variable in,
It's a local variable.
so it becomes automatically that
Yes.
you don't have to tell it, so it knows that it's a
any local variable will be in the register space.
so I have to be careful about how big it is. So,
Yes, if you define too many local variables, then maybe you won't have enough registers, and it will go to the global memory. But yes, so let's say we didn't see this, then I want to show you how Insight Compute could have helped us find this. So this is another program of NVIDIA called Insight Compute, which enables us to analyze a single kernel. So first of all, how do we use it? In order to use it, I'm running this on my local computer, and I'm connecting to a remote server where the GPU is running. So I need to add the application path and the working directory, and then I go here to filter, and I choose the kernel name that I wanted to analyze. And then here I choose the path where I wanted to save the report. And I also can choose in this metrics section which analysis sections I want. So there are many options. And I chose a few that I think are important. The occupancy section, the source counters. We'll go through them in a minute once we have a report. So yes, so these are the main things that you need to edit here in order to generate a report. This will also generate a command that you can just paste in the command line on the server itself instead of using this interface. I will say that sometimes you will need to go to the server to enable special permissions for this to be able to run remotely, which I've already done. But there's some information about this on the internet. Okay, so now once I hit the launch, the report is generated. And the report has multiple sections. So first we can see the summary of the bucket ACC naive kernel. We can see the time, 365 microseconds, the size, number of threads, number of blocks, cycles, and other details. this is just a summary, and it also tells us some general information about what could be some problems in this kernel that can make it faster. But usually, I go straight to the details. So what we can see here, first of all, is the compute throughput and the memory throughput. So we can see that the compute throughput is 16% and the memory throughput 78%. So it's dominated by the memory. And it tells you memory is more heavily utilized than compute. Look at this section to see what the bottleneck is. We can see the duration and other details. Yeah, there are actually many details in this report. I won't go over all of them. Also, this program inside Compute has many capabilities. Some of them I also haven't had the chance to check out. So another important thing is we can see the memory throughput here in the memory section, which is a 238. And this is actually low compared to the GPU's capabilities. The GPU's capabilities is around 1,000 gigabytes per second. So we see it's actually low. The important part that we can see here is in the warp statistics, warp cycles per issued instructions, 89, which is very high. It means that it issues an instruction only every 90 cycles. And it also tells you, on average, each warp of this kernel spends 43 cycles being stalled, waiting for the L2 instruction queue for local and global memory operations to be not full. This stalls occurs only when executing local or global memory instructions extremely frequently. So also this report tells you that you are accessing the global memory too many times. Okay. Another thing that we can see is if we look at the source counters, it will take us to the source section. And here we can actually see the PTX code that is generated for this kernel code. This is the PTX source code. And we can connect this with the actual CUDA code. And now if we press a line here, then we can see the line of code in CUDA. So you can see here that this operation yields a STG, which is a store command, and the load command. And it has also a sign here that, yes, 48% of this line's global accesses are excessive. So this also tells us that we access the global memory too many times. Okay. Any questions about this Inside Compute report?
Suppose you have many kernels, you still have one kernel by kernel.
Yeah, so what you usually do is you use Insight systems to get a view of the whole application. And then you see which are the kernels that take the most time. And then you dive into each kernel that needs optimization.
But you don't necessarily have that many kernels in an application.
No, I mean, just suppose you have.
I mean, a kernel
Like,
is like
you have
a chunk of code.
Yeah.
It runs many threads and has many blocks or whatever, but it's.
Yes, and also usually you're writing a new kernel, so you will focus on that kernel.
This is PTX or SAS?
I think it's the same. What's the difference?
I'm not sure.
I think it's just different names to the same thing, but I'm not completely sure. Anyway, this code is a general It's a general code that doesn't depend on the GPU, and this is further translated in the lower level to a code per the specific GPU. Okay. So moving on, we saw also from the code and from the report that we were using too many accesses to global memory, and now we improve the kernel using a register for storing the temporary result. So let's see what are the timings that we get now. Let's see. Yes, so we want to use this kernel call. Okay, now we get 0.1. We get 0.1. And if we compare this to the memory, it was 0.12, and now we're getting 0.124. So now we can see that we're completely, we reached the memory bound. So that means we're in a good place now when using the scalars. So yeah, so now if we look at this report, let's open. I already generated this report before. So I want to look at report 1 and to look at report 4. And another thing I can do is I compare two different reports. I can add baseline, and this is the original report. And now when I look at the second report, it's compared to the baseline. So the baseline was 370 microseconds, and now it's 90 microseconds. So it's a major improvement. And when we look at all the details, we can see that actually the compute throughput has increased dramatically. And now the memory and the compute are more evenly utilized. What we can also see is that this statistic with the warp state statistics, we had here 89, and now we have 19. So the situation is much better over here. We can also look at the source. So yes, it's still memory bound. That's why we see, but now we see that 0% of this line, global accesses are excessive. So this is also a good sign. Okay, so we looked at the report, and everything now looks better regarding this example with the scalars. Now I want to move on to see this kernel when instead of using it on the scalars, I want the buckets to use elliptical curve points. So now we use points, and let's measure the time. So now the kernel will do easy addition and not just modular addition.
That's a lot more memory.
Yes, the memory will also be, the points are larger than the scalars, but in comparison,
More.
yes. So if we test the compute, now we see that when we run the memory baseline, now we got 14.2 for the kernel. If we run the memory baseline, then we would get 0.5. And if we run the compute baseline, then we get,
So
we need to divide by 100. I can remind you, then we get 13.3. So we are much closer to the compute bound. So this kernel is a compute bound, but still, can you think of any way to optimize this kernel, knowing that it is compute bound? Maybe if someone knows the implementation of the MSM, he would know the way to optimize this. Anyone?
This is the equivalent of the final accumulator, right? Doubling the point.
No, it's equivalent of the bucket accumulation.
Doubling the point over and over.
No, it should resemble the summing all the points in a single bucket. It's just simplified because we are summing just a single point multiple times.
No, the kernel code doubles.
Yes, but well, what do we have here? We have a lot of buckets, and they are in different sizes. So that's not what I was going for. But we have
triangles and the rectangles.
no, never mind. What we have here is buckets with different sizes. So each thread does a different number of summations. And why is that a problem?
Wait for the worst one, right?
Yes, so the problem is we need to wait for the worst
Slowest.
thread. So let's look now at the report for this kernel with the EC points. And we can see in the report, which was a report number 3. Let's discard this baseline. What we can see here is we have a thread divergence. What does this mean? Instructions are executed in warps, which are groups of 32 threads. Optimal instruction throughput is achieved if all 32 threads of a warp execute the same instruction. And if we look at our kernel, and we go to this, again, the warp statistics section, we can see that the threads, active threads per warp, it's only 16 out of 32. And why is this? Because we have different sizes of buckets. So some of the threads will finish before other threads. And out of a group of 32, on average, 16 would be non-active because they have to wait for the other threads to finish.
Is there analysis?
It's we just have you need to imagine you have like different size of columns, tasks in different sizes, and some of the tasks finish later than the other.
It will also happen if you have like in the threads, if you have conditions, you could create divergence between threads. Because one thread will really do nothing, and the other one is going to have to do
The sizes
something.
are known in
Right.
advance.
And
Yes, the sizes are known in advance.
so the insight is presenting the statistics for a specific array of sizes.
Yeah.
For the run,
Oh,
it
for a
analyzes
specific
the
run.
run. Yes, yes.
So
But it's
why-
random, so we should
So why is
expect.
it on average and not deterministic?
On average, for every group of 32,
Oh,
we
okay.
run,
Okay.
yes, we run many groups of 32 threads. But on average, out of these 32, we can see this also in this section, the source counters. We can see that the branch efficiency is low and that we have many divergent branches. That's how we know this from the report. So, what could be the solution for this? Yes, thank you. If we sort the threads according to the bucket sizes, if we first sort the threads according to the bucket sizes, then we can have threads belonging to the same warp doing around the same average of the same task, length, size of task. So how do we do this? So what we do now is I'm using this function from the CUB library, which is called sort pairs descending. I want to sort the indices according to the sizes. So this function enables sorting two different arrays according to one of them. So we sort the sizes and the indices, and then we get essentially we get the indices array. Instead of being 0, 1, 2, 3, 4, it will be kind of scrambled according to the sizes. So the sizes would be in a descending order, and the indices will be scrambled. And now, when we send the sorted indices with the sorted sizes, we get
You're measuring the sorting as well.
yes, I'm measuring, including the sorting.
So there is a bit of effect.
But let's see the final result. So we get 7.8 compared to 14.2.
Makes sense. Because
So-
you had 16, you had about 16 out of 32, so it should be about half plus the sorting.
Exactly. So we managed to get around a 2x improvement. Okay. So that's all good. However, what could be the problems? Do you think this will also improve the scalars kernel?
No, because it's a memory problem.
Yes, but I mean, maybe it could improve it a little bit because you get rid of the divergence.
That's just no cost of
Right. So that's a problem. Now because we scrambled the indices, the memory accesses are random, and this will decrease the performance. So if I run now the scalar, it goes up to 0.5, which includes the sorting, and it's much worse than the 0.1 that we got before. But there could be a way to solve this too. How do you solve the divergence and the random access memory pattern? Are there any ideas? How could you solve them both? Using a different sort, maybe. So, yeah, so you could actually sort the buckets themselves. But I mean, it's kind of cheating because then you need to access the buckets in order to move them in memory. So the actual sort will take longer, but the kernel will be okay. But you do pay for the sort. So you could do the bucket sort instead of the indices sort. And then we do get a better time. For the kernel. Actually, yes, the time is worse because the sort is even heavier.
Longer.
Yes,
Because it's moved the data itself.
because it moves the data itself.
But if you do it on the curve,
But if you do it on the curve, then actually you can't do it. You get an out of memory problem because the actual sorting function is, yes, the sorting function can't work with as large as data as the points. But yeah, so if I'm gonna sum it all up in this table, yeah, so to sum it up, we started from the naive implementation, and we saw we got these times, and we compared to the memory and compute baseline. So we saw that the scalar was memory bound, and the point was compute bound. And then we made use of registers instead of reading and writing from global. And we got close to the memory baseline with the scalars. And this was the best solution for the scalars. And for the points, we were close to the computation bound, but we had thread divergence. And we solved that using sorting. And then we got a time of 7.8 for the sorting plus the kernel. And actually, the sorting is around 0.3.
Do you want to say something about there is a dithering solution that if you don't have many zeros, actually solves everything without sorting, right?
No,
You add
no,
the
that's
random-
a different thing.
Yeah, okay.
how do you deal with that, with the algorithm needs to be different for different types of, because your code is templates, right? And you need to do run different algorithms using the same code.
Yeah, so in this case, you would need two different kernels.
One for score, one for points.
In the actual MSM, we do this only for points. So we use this solution, the sorting. Okay, so actually, that's it for this session. Do you have any questions?
And again, like when you write just general question, like how do you when you write the MSN algorithm, right? Like it's like how do you differentiate between what stays in the shared memory and what stays in the global memory when you're doing the MSM algorithm? And these different stages, I assume it's as in the nodes, at least 3 levels of the algorithm, right? So where you have the first part where you have the bucket accumulation, and then the second part you have, and then the final combination where you just add them. Right. So, how do you decide where, when you do the bucket accumulation part, you use the shared memory only for the bucket accumulation part, and you define that, okay, certain number of buckets will be occupied in the shared memory. You finish them, you send it back to global, do the next, you go like this.
I don't actually use shared memory. I use only register memory.
Oh, completely. Okay.
Regarding shared memory, I will have an example in the next lecture, probably.
So general question is this. Okay, so when you have this hierarchy of memory, right? Like you have these 3.
Yes.
How do you decide what you will use for which part of the algorithm? What's the execution?
Yeah. So a good question. Usually, when you're working on large amounts of data, they will only fit in the global memory. So all your data is initially in global memory. The option for using shared memory and register memory is only within a kernel. so within a global function. But in your top function, all the data is in global. And only when you write a kernel, then you can copy some data from global to shared or to register space. And the shared is very limited by size. It's only for switching memory between close threads. And the register space is only a special memory per thread. So that's how it works.
If I can just not add, but maybe just like, point out like the registers are for a single thread. So there's no sharing between two threads on the same registers. The shared memory threads in the same kernel can actually access shared memory. So one can write, one can read, right? You can do, and then global can be shared by everyone. Okay, and the sizes differ. So sometimes the sizes matter, but a lot of times the functionality matters. Like if you don't need to share between threads, and the size makes sense, you'll do it in the register.
So it's like if there's protocols and stuff where you can do a lot of these things where they don't need access to share data, you can do it with directly with registers. And
I think that
so that makes sense. So the buckets don't really talk to one another till the next part.
I think the nicest algorithm is actually NTT, where you can see how the sharing makes sense at different levels. When you want like I don't know if Hadar is going to give you this as an example, but like the very, very small entities are thread level.
Mm-hmm.
So then when you want to create a bigger one from many threads, you go into share.
Yeah.
When you want to make the biggest one, you go into global.
Okay, anything else? Great, so thanks everyone for joining. I'll see you in the next session.
Thank you.
Thanks.
Thank you.
Starting